Most hardware projects fail, and they don't fail at the factory, not even at the prototype assembly stage. They fail much earlier because the founder and the engineer didn't actually agree on what they were building. No one defined the manufacturing goals or how to measure success, and most importantly, didn't write it down in the product specification. Welcome to Eugeneering, turning hardware ideas into mass production. Today I will show you exactly what a product specification covers and why skipping it cost founders 6 figures. Every development process starts with a solid foundation. And here's the problem. Founders often confuse two completely different documents, the business brief and the product specification. So, why do we need a product specification? First, to pull everything out of your head. All the ideas, visuals and sketches you have about the product. Second, to get you and the engineer on the same page, in measurable parameters that engineer must achieve. And third, to lock down decisions before development starts. Let's keep it simple. A product specification is the document where your product is described in 2 layers. First as functions, second as measurable results. Now, how big does this get in practice? Some automotive manufacturers like Renault, Daimler, VW and others issue a requirement pack of over 200 pages for a single hazard switch, the little triangle button that controls your car's emergency light. And that's just one input in a single product specification. Now imagine the whole document. The brief is the language of business, with a high-level description of what the product should do. It answers the basic questions. Why is this product needed? Who is it for? In what context will it be used? What user problem does it solve? What commercial goals does it achieve? That's it. No deep research, no concrete inputs for engineering. While the product specification is the strict language of engineers. Every line in the spec passes the 2-question test. What does it do? That's the function. How do we measure it? That's the measurement. What you don't measure, the engineer will guess. That's why the 2-question test make you do both. For example, what does the vending machine do? It dispenses items to customers after payment. It gives staff quick access for refilling. 2 main jobs the product has to do. One for the customer, one for the refill operator. Then, how do we measure it? Locking strength, 10 kilograms of holding force to protect items inside. Item drop time after the payment, 2 seconds max. Refill access for staff, under 10 seconds. And then secondary requirements, reliable, self-powered after loss of electricity. Runs 8 hours without charging. Under what environmental conditions? Temperature range -45 to +80. Humidity range from 10 to 90%. Space limitations 500 by 400 by 80 millimeters. How do we test it for real-world use? Drop test per ISO standard. Durability test 50,000 door open-close cycles. Here are 5 things we need to lock down before any engineer opens CAD. Target markets and industry. They determine certification. Production volumes. They determine manufacturing technology. Functionality defined by the 2-question test. Industrial design or visual reference. It shapes the final form. Timeline limits the project in time. Lock these 5 down and you have the foundation of a real product specification. Here's why that matters. This is not a bureaucratic piece of paper. This is your product's passport. Without it, you are guaranteed to burn money. Now, let me show you what a real one looks like step by step. Let's continue to break this down, but with a real example. Our task: develop a compact vending machine. Before we dive in, one principle that runs through this whole video. Finding the right question is half the work, and already a good result. So when I say finding, I usually mean a question we discovered, which is leading to something new that we could define in our future product. Here's our short brief, without commercial goals, just to keep it simple. This is a small vending machine designed to operate in LTE 3G coverage zones. Dimensions are 500 by 400 by 80 millimeters, featuring 20 internal compartments. Operated through a dedicated web app. We want to print it using FDM technology, but in the future quickly switch to injection molding, so it will be designed for both technologies. We're manufacturing 50 units with FDM printing now, with injection molding planned for scale-up. The key decision here, designing for both technologies from start, that gives us a cheap MVP and future scaling without redesign. That's already one of 5 things from our checklist. Volumes and technology that are locked down. Timeline. We need the prototype ready for testing on the 1st of August to participate in a startup event and do the testing before the event. Industrial design. Visual references will not be provided now for this MVP. We prioritize function over form. Anything aesthetic adds complexity. Visual adjustment come later, handled with AI design tools after the functional part is finished. Our target market is European Union, so European conformity marking, waste electrical and electronic equipment, and restriction of hazardous substances is mandatory. But some certifications depends on components used in the system, so we can't finalize the full list yet. And that is our first finding from this point, an open topic. Now, functionality, the biggest topic. First we do the walkthrough of the user journey, step by step, action by action. We identify 3 categories of users: the end customer, the operator, and the system admin. Let's take the end customer. The customer sees the machine, and here's the first question. Do we want ads on it? How does the customer understand that there is something inside? Then the customer scans the QR code and gets to the page with the items. How should it look? Do we want to create a personal account for the customer? That's another finding. We will decide when and what to answer later. Then, the customer picks an item. Are we allowing the customer to take several items at the same time or only one by one? What does the app look like? Then the customer pays. How do we make a payment safe? What are the requirements for that? Which system we will use? Google Pay, Stripe, etc. Then the customer takes the product out of the machine. How does the door close after the customer takes the product? Every one of these questions becomes a requirement in the product specification, and that's the main finding of this thought experiment. Now, knowing the purchasing path, we can go through the standardized list of the product specification chapters. We divide the technical part into segments: electronics, mechanics, software, the basic one. Electronics, power, 110 to 120 volts, most universal standard. Door opening time, under 2 seconds after command. Beyond 2 seconds, users start wondering if the machine is broken. Failure rate, strictly under 0.01%, or 1 failure per 10,000 cycles, including software, mechanics, and electronics. Mechanics chapter. Protection. IP41, because of indoor use. Higher protection adds costs without benefit. Then weight. Under 4 kilograms. For a single person installation. Easy to ship as a parcel as well. Material. Flame retardant, transparent plastic. Fire safety plus product visibility from outside. Door operation. Manual closing by the user, no automatic mechanism. The door stays open if the customer doesn't close it. I understand that it's not ideal for UX, but acceptable for MVP. Software chapter. No code app during the MVP stage to keep costs low and development fast. Data. No personal data storage on device. GDPR compliance simplified. No data controller obligations. Then performance. Transaction processing under 1 second. Keeps user experience responsive. App design according to the provided mockup in Figma. There are also standard chapters we won't cover today. Testing, regulations, unit economics, procurement, project planning. Each may get its own video. And now for the most interesting part, the question that pops up during the spec drafting stage. How do you launch your project fast and cheap, make it look like a real industrial product, and still be safe? That's exactly what we are covering in the next videos. Now, the part most founders find out the hard way. Remember when I said skipping the spec cost founders 6 figures? Here is exactly how. There are the 6 hidden risks that turn hardware projects into financial black holes, even if you have a perfectly working prototype in your hands. Each one is easy to prevent if it's in the product specification. Each one devastating if it isn't. That's why this document matters. First one, the gap between prototype and mass production. The biggest misconception: I have a design for 3D printing, so we can start scaling with injection molding. That's a costly mistake. Injection molding is a completely different technology with shrinkage, weld lines and draft angles that don't exist in 3D printing. In 90% of cases, what works on a printer doesn't work for injection molding. If you don't design for both technologies from the start, expect to pay 2 to to 5 times what you have already invested and start the project over. Second, belated DFM. A founder spends 5 to 10k on industrial design, falls in love with the shape. Then the manufacturer says, this isn't manufacturable, not feasible. We need to redesign it. DFM has to run in parallel with industrial design, not after it. Third point, tolerances or GD&T. 2 3D printed parts fit together perfectly by hand. But when a factory produces 5,000 units with a tolerance range of 0.15 mm, half of your batch simply won't assemble. And most founders never even think about this until it's too late. 4. Certification. Most founders only remember certification when the product is already finished. As a result, to pass the tests, you have to shield the PCB, change the plastic, or adjust clearances, which sets the project back by a month. Tooling economics and minimum order quantity. You're thrilled that a plastic enclosure costs $3 per part, but you also have to pay for injection molds, and that's 3 to 90k per mold, depending on complexity, of course. Then the unit economics collapse. And one more tip. Always ask the supplier to quote the mold cost and the unit price separately. That's way your unit price stays low and future orders cheaper, because you have already paid for the tooling. Then, the cost of late iterations. Saying, let's move this wall by 2 mm at the drafting stage costs you nothing. After tooling, the same change means remaking the mold from scratch. Same cost, same lead time, all over again. 6 risks, 6 expensive lessons, all preventable if they're in the product specification. Let's do a quick recap. Here's the good news. A successful hardware project isn't a luck. It's a process you can learn. First, log down your project inputs, volumes, timelines, design, markets, functionality, before anything else. Second, write a product specification together with an engineer. Don't stop at the brief. Third, run design for manufacturability in a parallel with industrial design, not after it. And finally, the 2-question test that ties all of this together. Build a habit to it. Every function, every requirement, every decision, every parameter answers the same question. How do we measure it? That's the engineer's mindset. Apply it on every project. If you are working on a hardware product right now, subscribe. We cover the full hardware journey on this channel, from the concept to mass production. And let me know in the comments what's the most expensive hardware mistake you've ever had. Yours or someone else. Drop it in the comments. In the next video I will dive into the brainstorming process and show how we generate innovative concepts and solutions. See you there!